So the topic of my talk is this molecular Kondo regime, but now I would like to take it from a little bit different perspective and use this combined AFM STM measurements and see more in the direction of the forces. And actually this work is done in collaboration between the Institute of Physics in Prague, then the original work on this PTCDA molecule on the silver was done already in the group of Stefan Tauc and Ruslan Temirov, and also we had some support from the Markus Ternes code to understand a little bit these interactions. Okay, so what I want to show here, okay, we have this STM, which mostly of these works were done with STM, but the question is, okay, these days we can combine STM with AFM, so we can measure at the same time forces and the current, and what we can get more from this, okay? So there are some questions. I mean, of course, there is a question of atomic contrast. If we do the STM AFM on the same object with the same tip, do we get the same? Mostly not, okay, so but there is some question, there is some competition between these two things, and basically to have two channels we can get more information about the objects which you want. So this is, for example here, the combination AFM and STM allows us to distinguish the molecules sitting on semiconductors which usually are blind to STM, but is with combination AFM you can really distinguish between molecules, hydrogen, etc. There is also another challenge in the community of this molecular electronics. So when we gate the molecule, we don't know how good is the gating. Or there is a second advantage, or the second challenge is basically we want to understand recently forces which are induced by the current which goes through. So basically this is the ideal case where we measure simultaneously force and the current as a function of the bias and the distance. And finally, also we have this electrical and mechanical system where we couple the electronic degree of freedom with some mechanical oscillations. Okay, so these days what basically we can do, we have different techniques how to do this. So either we use these quartz sensors, either Colibri or Q+, or traditional silicon cantilevers technique where they are coated somehow, so basically you feel at the same time force, current. And also a part of this you can get also the dissipation signal, which will be important in my talk. So basically the dissipation signal is, to explain it, when we are oscillating is the driving oscillator which is kept in the constant amplitude, but the frequency is changing. But of course if there are some non-conservative forces acting during the oscillation, it means when you oscillate and the force which you acting on your probe is different when you're approaching and when you are retracting, basically then you have some dissipation. So you have to basically keep the amplitude oscillation constant, and this is the energy which you store to your cantilever to keep the energy oscillation constant. Okay. So also, as I mentioned, these days we can also do some kind of advanced spectroscopies where we approach tip towards to the molecule and we measure the current and the frequency shift as a function of the bias and the distance. Okay, so here I will introduce this PTCDA on the silver 111. So the PTCDA is the German molecule. So I was told by Ruslan that every German group has to measure this. I don't know if it's true, but we are from Czech, so we try to. The thing is, basically, this PTCDA is a kind of acceptor. So when we put it on the silver, the LUMO molecule is below the Fermi level, so there is a charge transfer from the surface to these LUMO orbitals, and it means that now we have LUMO orbitals which is almost occupied by 2 electrons. There is some back donation, but that's not too important. But the important thing is when we start to withdraw the molecule from the surface, so we gate the molecule by this oxygen which is on the periphery. Basically now you start to modulate the occupancy of the LUMO at certain position. When you start to withdraw it, what happens is that basically now you jump to the regime. The LUMO goes towards to the Fermi level, and you go to the regime where you have single occupied electron in LUMO, and then you have, let's say, this Hubbard satellite LUMO plus 1 plus U above the Fermi level, and this gives rise to the strong peak or strong Kondo regime which it was observed here by STM. Now using this combination of AFM and STM, you can get very precise control on the distance and also measure the forces during the retraction. So you can correlate at the same time the forces, or if you want the frequency shift, which is in the first approximation, the gradient of the force and the conductance. So in this, basically in this talk, I'm going to use this combined technique to really investigate this system, looking at the, let's say, the coupling of this electrical and mechanical movement. So first of all, first motivation is actually when I'm retracting the molecule from the surface, I go from the strongly coupling regime, or let's say Kondo strongly coupled regime, to the weakly coupling regime, and I can really modulate this, these two regimes by the withdrawal of the PTCDA from the surface. And the second motivation here was actually there is a recent theoretical paper, or there are two papers from the same people, where they claim that actually this Kondo, some modulation of Kondo can be used to mechanically excite the cantilever here. So the idea is basically that we have oscillating cantilever where there is this quantum dot which has a Kondo regime, and basically now due to this long relaxation dynamical of the screen of the clouds of Kondo, basically you can get some coupling in between. Okay, but of course then there will be two regimes which would be manifested somehow in the fact that you will dump your oscillation. It means if your let's say fluctuation of the electron clouds from the Kondo would be in anti-resonance with your oscillation, or even if you tune it properly, then you can even excite artificially this cantilever. So it basically it will be coupled this electronical Kondo to transfer the to the mechanical motion. Okay, so to do that we use our JT SPECS machine, where we use this colibri sensor, which allows us to combine AFM and STM. It's in low temperature, and also the important thing is with magnetic field, so we can apply this magnetic field perpendicular to the sample up to 3 Tesla. So basically with that also we can get these high resolution images when we functionalize properly our tip. So this is this PTCDA which I'm going to investigate. This is monolayer of PTCDA, and again with the frequency shift, the current, I can get this high resolution contrast. But that's not the subject of this talk. And apart of this, we will also measure also this using the locking techniques with the IDV spectroscopy at the moment. And these are the standard technique how to prepare the silver sample and also the deposition of the molecule. Okay, now about the spectroscopy, we have two options how to do this. Okay, so basically here all the time what I'm going to do is to withdraw the molecule or lift up the molecule on the edge of the island of PTCDA's molecule. So this is the clean silver surface 111, and this is the edge of the molecular islands, and I will pick up in particular this molecule, and after all the spectroscopy I check that nothing happens. So you see this is the STM image taken after the spectroscopy, and you see that basically nothing happened. Okay, and this is how we contact the molecule. So we approach over this side, let's say after normal scanning the feedback is off, and then we approach the tip, and then we see the characteristic jump, and then also in the frequency shift we see some kind of so this is the traditional approach where you see this kind of attractive forces, and then there is a jump, and from that you will start to see something more complicated than it was before. And this is the signature. We actually gauge the molecule now, and we can do these experiments. So now there are two ways how we can do these experiments, and you see there is a slight difference, but not too big. So basically first we can come and we will just pick up the molecule at different bias voltages. So we go, let's say, from minus 15 millivolts to plus 15 millivolts, and we will just have good resolution in Z, but also the resolution and energy will be a little bit worse. So for this reason we can do also another procedure, is that we will contact the molecule, we will start to pull off, and we will stop in each distance, in Z distance, and we will just ramp the bias voltage and measure this locking technique. Okay, so these are two different techniques or two different kinds of approaches how to do these spectroscopies. So this is the result. So I just show you few of these slides here to don't mess up too much. But basically in far distance regime you see there is a no Kondo signature, but then we start to pull up. The LUMO is approaching towards to the Fermi level, and certain moments the Kondo peak appears, and then we pull out away, and then you see that the Kondo is getting smaller and smaller. And then basically, well, we stop and then we go back and forth to don't lose the molecule. So these are the, let's say, force field calculations using classical potentials which allows us to somehow to resample the configuration, because for DFT this would be probably too heavy. And we see that basically there is a nice agreement between the force, the frequency shift which we calculated, and the one which I've shown here. Sorry, it's just in reverse in both cases. But basically from that we can understand, and each position what's the, let's say, what's the geometry. Okay, so we start here where we are out of the Kondo, so basically this would correspond to this situation. Then we approach closer, then now the molecule starts a little bit slide. So this step here, it's, let's say, kind of sliding of the molecule over the surface, and then we go further and you see we are retracting the molecule. So the final state that we are here is basically almost the lift up the molecule, but still gated by both tip and the sample. Okay, so from that I can also show you, you can identify where we start to see this Kondo regime, which is actually here. And the next step basically is, okay, I can show you now different sessions. So that's the difference, let's say, between this first set which was taken with this Z spectroscopy, and then you see indeed that basically for there are not so much difference. So there are different sessions on different molecules with different kind of tips. You see that the magnitude of the current is changing a little bit, but basically this Kondo regime is pretty stable. So basically there are some differences in the way how we gauge the molecule, but all the time was the molecule which we pull away from let's say the edge of the island. Okay, so now let's have a look on the magnetic on the effect of magnetic field. So now to keep it as much as reproducible, basically again what we do is we take the one spectra with the same tip on the same molecule in one magnetic field, then we just stop the one set, we erase the magnetic field, and we go so on from 0 up to 2.8 Tesla. So basically you see in one Tesla there is some suppress of the Kondo in, let's say, in far distance regime, but with 2.8 Tesla we reach the regime at certain distance where we are able to split the Kondo. Okay, it means that we go from this strongly coupled regime to the weakly coupled regime, which is modulated just by the mechanical action or the fact that basically we are decoupling this Kondo orbital. Okay, so again from that we can estimate where is this strong Kondo regime and where is this weak Kondo regime, and this is basically pretty stable for different sets of the measurements. Okay, so this is just show you this overview. So this is just normalized conductance for 3 different sets which we have been measuring for different magnetic fields. So you see at 0 magnetic field there is a strong Kondo peak, and when we apply magnetic field about 2 Tesla we are able to split this peak at certain distance. And as I told you, basically the distance where we are splitting this Kondo regime, where we go from the strong to weak coupling regime, is basically at the same distance. Okay, so but with this technique we are taking not only, let's say, the DIV or the current, also the frequency shift and the dissipation signal. And the dissipation signal is would be important if I report this kind of like Kondo drive mechanical coupling. So basically any instability introduced by this Kondo would be reflected in the dissipation signal. So that was one of the aims of our simulation here, was to see if we are really able to somehow induce this coupling between the Kondo and this mechanical oscillation. But unfortunately this is not the case. So again I will show you here this frequency shift for the same sets, or let's say same tip, and this is the dissipation signal. Okay, so you see basically the dissipation signal doesn't change too much along the trajectories. I mean there is some deviation, but this is very small. It's below the 1 milli eV. So basically you see that some kind of mechanical distortion of the tip is making much larger impact on the dissipation than basically some kind of induced Kondo force due to this modulation. So and then also if you look on the mechanical gating, I mean, you see that also we do not see any significant trend when we arise the magnetic field. So it means when we, let's say, split the Kondo, again there is no signature basically about some Kondo effect or a Kondo force acting on the tip. Of course, all these differences which you see here are due to a little bit different gating than some kind of Kondo force. Okay, so basically so far our experiment can't prove that this theoretical prediction, or I mean at least in our parameters which we have been using for the oscillation, this kind of coupling is not possible. But now I would like to go back a little bit and use this Marcus code and see what we can learn from, let's say, to take some informations about this, okay? So I will be analyzing, we know that actually this Marcus stuff doesn't work in the strong coupling regime, so I would like to focus basically on this regime where we split the Kondo and see how the fits are good or bad. Okay, there is one more thing which I should mention. We also estimate this Kondo temperature as a function of distance, and there is some small surprise here. So basically we use the Frotta function, then we also from the Frotta we can get this Kondo temperature, including this correction to the experimental temperature. In our case the experimental temperature is 1.2 Kelvin, but what we found is something strange. So basically if you calculate this temperature, you will see that, well, in closed distance regime, of course, the Kondo temperature is pretty high, but when we get, let's say, to 350 picometers, already the Kondo temperature is about the minima, okay? But then we pull away, here we still see the strong Kondo, we are not able to split this peak, but basically we have to move away, and then also the Kondos, the temperatures start to increase, okay? But the splitting happened somewhere here. So it means that normally one would expect that the splitting should happen here because the Kondo temperature is already small. I mean, we do not understand properly what's going on here. One of the things can be, which I will mention later, is actually that here we have a molecule which is strongly gated to the system. So basically we have like quantum dot, which is a little bit different, and probably the coupling to the tip can make some other assumptions here. Okay, so now about the fitting. So here I show you this region here for different magnetic fields of the same session, and basically the idea here is to keep the parameters somehow reliable. It means that basically we want, you know, I mean you can do the fit each distance, but basically you want to see some trends, okay? And that's the best what we can get. I mean, so you see that basically the fit works pretty well when we are in this weakly coupling regime, but when we get the strongly coupling regime, on the onset of the strongly coupling regime here, you see that the code or this single perturbation theory is no longer able to reproduce well like this stronger peak. But the nice thing is, if I restrict really myself to this regime, is that basically you see that the fits are pretty stable. So it means when I go from one distance to other distance, basically it has some trends. So for example, this J rho is somehow decay exponentially, and also this T square, which is just the hopping, also it behaves in a good way. It means because we are kind of retracting, so one would expect that basically this should also depends on the exponents. Okay. So basically what you see that the J rho somehow is linearly proportional in this regime to the T square, which I think is also some kind of reasonable way.
J rho negative means ferromagnetic?
Yes, antiferromagnetic, yeah, exactly, yeah. So then, okay, sorry, what's this? Okay, so now I can take another image, another set, and actually here what happened is, if you look in the frequency shift, the zero magnetic field was gated a little bit differently. Okay, so basically what you see, actually these two guys were basically, we were lucky and we were gating in the same position, but here was a little bit different. But nicely again, you see that this J rho here is actually again behaves a little bit differentially, which is also reflected here. So we see that basically these two parameters are somehow connected. In this fit, I have to say I fix at beginning, I fit the G to be 2, because if I release this one, that the fit start to be really crappy. And I think that, okay, it can be some reason to change G, but basically to make it simple, I would keep it constant. And the second thing, of course, I would like to mention that, that here I use the U, this Coulombic scattering plus, because you see the asymmetry goes on the left, on the right, sorry. But in other set, basically I have to use the minus 0.3. So basically it seems that it's changed from time to time. Okay, so there are my comments on this. So first off, the question of G factor renormalization. I mean, there's an old paper where basically say that this G should be renormalized according to J rho. And that's actually what we see here. So if you are in far distance regime where this J rho is negligible, basically there is just like linear splitting. But then when we go close to this regime where J rho start to increase, basically then there should be some correction to the G naught. There is another question. Of course, we are lifting up this molecule from the surface, so LUMO start to feel different environments. So the screening of the molecule of the LUMO is different. So then also it should contribute somehow to the G factor. Now about this Coulombic, I said that for different sets we see actually positive, negative, or even zero. So how we can understand this, and we know that we are picking up the same molecule. So basically, what means it must be effect of the tip gating somehow, because the molecule is more or less all the time the same. So basically what we believe is, again, you can go back to this old Wolf-Schrieffer Anderson mapping to the Kondo, and basically you see that U here, it can be written in this form. So again, I think the U here, it means kind of asymmetry or this electron hole symmetry here. So basically, if you are gating in some way, if the let's say this LUMO and LUMO plus U is somehow asymmetrically positioning with respect to the Fermi level, this gives you rise to this U. Okay, so then in this weak coupling regime, I already shown that basically J rho and T are somehow proportional, and both they scale as a exponential function. And I think my main problem here is that actually the Marcus code is working in the regime where basically you have the molecule sitting on the surface, and then you have tip, which is basically not touching. I mean, we are in very far distance regime, in the tunneling regime. But here, this is kind of different. Here we have a molecule which is gated by the surface and the tip. And then basically you have to, if you want to express this transport through the molecule, you have to consider both couplings to be at least somehow equivalent. So basically then you have to use this formula from the molecular electronics. And then the question is, of course, how important is actually, let's say now you can think about, I have a two Kondo screening. One is on the surface and another one is on the tip. So I have a 1,4, it's this elevated TK when we are getting away. So basically when basically the tip is more strongly bounded to the tip, then the molecule is more strongly bounded to the tip than to the surface. But on the other hand, basically if you look on the mechanism how the molecule is bounded to the tip is basically through these oxygens. But the LUMO is basically P-like kind of system, which is mostly on the central part. Okay, so basically all the Kondo is happening just through this molecule, and the coupling between, let's say, the metallic states on the tip to this P state in the configuration we have is very weak. Okay, so from this, I think this is the reason somehow why this could work, this Marcus code. Well, actually, recently we are working, doing these NRG calculations to understand in more details, and also, I mean, we are discussing with Marcus how to adjust the code to really adjust it to this kind of system, and we will see if we can get some better agreement. Okay, so at the end, this is the conclusion. I think this AFM STM can provide more details. Unfortunately, we were not able to prove this Kondo impact on the mechanical oscillation. And but on the other hand, with this mechanical stress or the mechanical force, we are able to tune the Kondo regime going from the strong to weakly coupling regime. And basically, thank you very much for your attention.